Okay, I want to wrap up our discussion about cyclohexane and in particular chair flipping, and we're also going to talk about stability. Which of the two chair conformations is more stable, or are they of equal energy? Now, in the previous video, I left off the video with a particular problem. So this is recall. This is video 01F, I think, 60. Okay. And we started the problem, but we didn't quite finish it. And the problem was you have this molecule, cyclohexane, with a wedge bromine, a dash chlorine, and the problem was draw the two chair conformations. The trick for this is go ahead and set up your templates. I like to draw my chairs with the butt of the chair being completely horizontal. The textbook has it a little bit tilted. And then make sure you have a lot of space because you don't want groups hitting each other from the two different conformations. Now I'll draw the other chair. Okay, pretty decent. Okay, so the trick was, remember that we get to decide what the wedges and dashes mean in terms of direction. And I like to say wedge means up. So if a wedge on the flat cyclohexane is shown, then it would be up on the chair conformation. Dash equals down. The other tip is to number your ring. Okay. Not based on nomenclature, but just on convenience, on where you want carbon number 1 to be. Because I like carbon number 1 to be in the northeast corner for this particular template. So what's important, and we did go over this in the previous video, 01F60, is do you know what what up is in carbon number 1? Is up in an axial orientation or equatorial? And because it has to be up, because that's how I defined this drawing. Now, obviously, your classmate could say, well, what if I indicate wedges down? I mean, that's perfectly fine, because with a model, for instance here, let's say the blue atom is bromine, so it's coming towards us. Well, they could orient the chair like this. They could orient the chair like this. So that blue atom could either be up or down. The point is, be consistent. Okay? If you choose it to be up, always keep it up. On carbon number 1, okay, bromine up is in the axial position. Axial up. What that means is that this hydrogen off the same carbon is equatorial down. And you want to draw, right? You want to draw your chairs so you see tetrahedral carbons. Equatorial down. Okay. The next issue is where's carbon number 2? Because 2 could either be here or it could be here. But if you think about your drawing, my 2 is to the right. Okay. So when it's a little bit difficult without a model, but if you take, for instance, I don't know, maybe this thing right there, this white out, and you look and you say 2 is on here, that's the right hand side. For bromine to be up, I'm pushing it like that. So see, that 2 carbon is actually the one closest to us. This is 2 here. There are other ways to verify that for yourself. Obviously, you could use a model, okay, or you could try to visualize this rotating and laying down on its side. If I take this molecule that's flat on the paper with my hand and I do this, like that, that bond right there is this bond, the 2,3 bond here. So it's the one in front. Okay. Chlorine is dash, and I'm going to indicate that in the chair conformation that will be down, but we have to decide, is it axial down or equatorial down? And if you remember your template, it's equatorial down, like this. Okay, and that's how far we got. So if you're a little bit behind, or you're not understanding how we got this fairly quickly, go back to this video, because in this video we drew out all the hydrogens with the proper axial, equatorial, up and down designations. So this chlorine is going to be equatorial down. So these are the two atoms that I'm interested in. And that's where we ended off on the last video. To do this inner conversion, it's called a chair flip. Chair flip. To do this inner conversion, literally, you take your molecule. Okay, so let me start out from the flat version first, from scratch. A little bit difficult. Okay, so there's flat. See that bromine blue? That's the wedge. Chlorine here, I made it yellow, so it stands out away from us. I took the molecule like this, and I made the head on my right and the feet on the left. And I kind of straightened it out a little bit to make sure that I see some axial hydrogen. Do you see that bromine axial up? This chlorine equatorial down. So the model matches this drawing right here. Without breaking any bonds, because this is equilibrium, we're not changing the molecule. We're not changing the identity of the molecule. But we are twisting bonds to get to the other chair conformation. And the easiest way to twist those bonds is to do this. You take carbon number 1, the head, and you make it the feet. You take carbon number 4, the feet, and you make it the head. Okay. So here's carbon number 1, the one attached to the blue atom, and I'll make it the feet. So push it down, 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 down. And then here's carbon number 4, and I'm making it the head, so I'm going to push it up. Okay. And if your models are like mine, these are called the HGS models, it probably will kind of snap into place, because remember the flat version has angle strain, right? When the geometries are flat, that angle is 120 degrees, 120. That's kind of far from 109.5, the tetrahedral. Now, did you see what occurred? Look at my blue atom now. It's still up. My yellow atom, it's still down. But what changed? This is now equatorial. So let's go back to the original chair, right, like that. Okay. And then I'm going to keep an eye on this blue atom. Down. To keep an eye on this yellow atom. And it snaps into place. What's important also is knowing that we're shifting this carbon down. Hopefully it's apparent that that's carbon number 1. Okay. But did you see where carbon number 2 is? See this carbon number 2, when I go back to the original molecule, that carbon number 2 is right here. Okay, keep an eye on this carbon number 2. When I do the chair flip, do you see where carbon number 2 is? Carbon number 2 is still in the front. Still in the front. A lot of people make the mistake and say this is carbon number 2. That's not right. This is carbon number 2. Right here. That's carbon number 2. And this is carbon number 3. Okay, let me zoom in. Okay, we'll put the models aside. That's tricky. Okay, I know that this is a lot of people are tempted to put carbon number 2 here because it's further to the right. This dot, just like this dot, is further to the right. But what do you want to keep in mind? See this bond right here? I'm going to make it bold. that bond is actually the bond closest to us when we have the model to its side, like this. See, that 2,3 bond is right here. So I'm going to do this kind of fast. Keep an eye on this bond. Okay, I want to do the chair flip. Do you see how it's still in the front? Let me try this again. Yikes. These two carbons are always in the front. Those are the 2,3 carbons. See, this bond here, which is, the 5,6 bond, that's always in the back. 4, 5, 6. Okay? Now, let's go to the substituents. Do you realize that the bromine still stayed up? But now, on this carbon, in this chair template, the up position is equatorial. Equatorial up. And obviously, hopefully, the hydrogen is axial down on the same carbon. On carbon number 3, okay, let's try to predict this. Okay, I know you saw the models, but when we did a chair flip, the up stayed up, and the axial toggles to the equatorial. When you do the chair flip, you can say that when you flip, up stays up, down stays down, down stays down. And what are you doing? You're toggling. You're going back and forth between axial and equatorial. Okay. So here we have chlorine, equatorial down. We could say that it has to still be down because it's always going to be dash, and that's our convention. So we could always go back to this carbon 3 and say, well, is the down position equatorial or axial? Okay, so that's one way to do it. But the other way is if you're confident with your first drawing, you toggle the axial and equatorial and you keep it down. So this is going to be axial down, axial down. So by using this rule, and also your models, you have this axial down. What that means is that, can you see where the hydrogen is now? The hydrogen is equatorial up, because that is a tetrahedral carbon right there also. Okay, it's a little bit harder to see because it's not one of these corners, the upper corner or the lower corner, but this is tetrahedral. It does follow our rule, so this is now axial down, down stays down, toggle axial equatorial. And finally, we could go to the model. So here is, zoom out. So here is the model for the chair conformation on the right. There's your chlorine. Axial down. There's your carbon 2,3 bond right here. Okay. Bromine, equatorial up. Okay. Now, is it possible that your classmate will draw this one first and then toggle to this? Yes. Is it possible that your classmate can say, well, I want chlorine to be carbon number 1, and I want chlorine to be in the upper northeast corner? Perfectly fine. You know, it's a molecule. They could draw it like this. They could draw it rotated, any which way. They could even draw it upside down from your drawing. As a professor, what I like to do a lot of times is I force them to draw a certain conformation by putting in one of the substituents. Because if I put in the bromine and I ask you, then I could ask where's the chlorine, everyone should put the chlorine right here in the equatorial down position. Relative, right? It's relative to where the bromine is. But if you're drawing from scratch, you choose whatever is convenient to be carbon number 1. Okay, so that's an example of drawing 2 chair conformations from a flat wedge dash drawing. The next thing I want to discuss is stability. And if I have this molecule here, okay, and I'm going to put a methyl group, and I know this carbon is not, how should I describe this? Well, let me just draw it wedged. I was going to talk a little bit about, it's called stereochemistry, but at this point, many people, when they get to this part of the class do not know much about stereochemistry. But you do know this. If that is wedge, okay, what does that hydrogen have to be? Right? So let me just do this real quickly. Put a methyl group, and I'm going to make this molecule flat. So here's my methyl group. Zoom out, make it flat, okay, push it down on the paper. Okay, so there's my molecule. There's the methyl group coming towards us. Okay, we haven't had much practice in prior videos, but do you see where that hydrogen is? It's away from us. It's in the back. So you'll get used to this. Even though they don't draw the hydrogen, we can add it if we want, but we have to add it as a dash. Okay. Let's draw the two chair conformations. Okay. I know it only has one substituent, but let's see if our two chair conformations are identical or not. There will be times where the two chairs are identical in terms of how they look, in terms of their energy, etc. But let me draw the two chairs, and we'll verify whether they're identical or not. Okay. See the strategy? I drew the two templates first, and then wedge means up. So I'm going to make this methyl group up here, draw this hydrogen here. I'm going to label this carbon number 1, and just so I orient myself, carbon number 2, even though there's no second substituent, because I want to make sure that this is carbon number 2, this is carbon number 1. I started out as axial up, so it's going to toggle to equatorial up. And your hydrogen now is axial down. It's in equilibrium, okay? But we have to think about now stability. We've seen strain before. What are the three strains that we've seen previously? We've seen torsional, but that's not going to matter in this case because none of the groups on the carbon-carbon bond are eclipsing. They're all staggered, actually, right? When you make a chair conformation, right, everything is staggered when you look down any carbon-carbon bond. That's the beauty, actually, of cyclohexane in the chair conformation. Everything is staggered. So that's torsional strain. We don't have any. No torsional strain. Then we have steric strain. Question mark. Do we have any steric strain? And then there's angle strain. Oh, no question mark. There's no angle strain because we took this flat cyclohexane, which has a bond angle, internal bond angle of 120. When we make it into chair, right, everything's tetrahedral. Everything's looking actually perfectly tetrahedral, each of these carbons. Okay. I put a question mark here because I know there's actually steric strain, and it may be a little bit hard to see where that steric strain is. Okay. Let me show you. It's kind of a unique type of steric strain. It's called 1,3 diaxial strain, and it is a bumping strain. Steric strain. Okay. I don't see anything bumping in my drawing. This one right here. Well, the bumping is this. See, my methyl group is straight up, axial up, and as this methyl group rotates, okay, it's actually getting really close to these two hydrogens that are 3 carbons away. How do I want to say this? So if this is carbon number 1, the second carbon, the third carbon. So this hydrogen is straight up and down. If I go count the other way, this is carbon number 1, the second carbon, the third carbon. So when they say something like 1,3, it's the relationship. It's the hydrogen on the third carbon relative to the group on the first carbon. So I'm going to maybe put a little circle here. Okay. So what is that strain? Okay. Does it really exist? Because the hydrogen on the 3 position is here, and the hydrogen on the 5 position is here. So the way I numbered it, I do realize that this is carbon number 5 right here. But in relationship to this carbon, it's the 3rd carbon. 1st, 2nd, 3rd. 1st, 2nd, 3rd. To indicate this bumping strain, you could do something like this. Okay. I know they look kind of far on the paper, and they actually kind of look, they don't look that bad in real life, well, in models. But remember, these hydrogens have some heft to them. They have some bulk. So you're going to be bumping. Now, well, that means that if this is bad, when the group is in the axial position, does it really relieve stress when I put it in the equatorial? Because when I do a chair flip, the methyl group is now out here. Well, let's take a look at that. There's my methyl group. Sorry, there's my methyl group, and I'm going to do a chair flip. Take the head, which is on the right, make it the feet. Take the feet, which is on the left, make it the head, like this. Okay. Okay. So now, I know it's a little bit hard to see. You should be using your models as well. So there's your chair conformation. Look at my methyl group. My methyl group is way off to the side, and as this methyl group rotates, it's actually not that close to any of the hydrogens. Okay? At least relative to this conformation here. So there is no 1,3 diaxial strain here. No 1,3 diaxial strain. Okay. Not sure what's going on with my camera. It's a little bit, the exposure is really high. Okay. So, which is the most stable conformation? This was. This is more stable. Okay, because it has less big groups in the axial position. So this has no axial groups. Now, I know that we have hydrogens that are axial, but hydrogen, they don't bump into each other when they're axial. Hydrogen is small enough. But when you start replacing that hydrogen, okay, with a methyl group, then you start to favor the conformation where the group is in the equatorial position. Okay, so you're trying to minimize, right? Minimize the number of axial groups. Now, what happens if we have a tie? Okay, you know, if I had put a methyl group, well, let me show you. Instead of trying to visualize it in my head and making a mistake, let me show you where it can be a tie. Methyl group here. Okay. For it to be a complete tie, we have to have 2 of the same groups. And maybe I can put a dash here. Okay. 1, 2, 3. I'm doing this a little bit fast, but you could definitely pause the video and you could draw me the 2 chair conformations and test yourself. Okay. So you could pause now, draw the 2 chair conformations. Alright, welcome back. If you have this chair like this, and I'm thinking carbon 1 is right here, wedge is up for me, that's how I like to think of it. I have that, and then carbon number 3 dashes down, but is it down axial or down equatorial? It's down equatorial, CH3. Okay. When we do the chair flip, you're flipping this carbon down and flipping this carbon up. You're not breaking any bonds. You could do the chair flip without breaking any of the bonds in your model. So again, not the best at the chair drawing in this case. Ugh. That's so embarrassing. So here's one of the methyl groups that's circled in pink. We'll keep an eye on that. Axial up, equatorial up. Carbon number 3 is this one right here. Carbon number 2, carbon number 1. It starts as equatorial down, so it should be axial down. Okay. Mark your carbons. Okay. What did I notice here? One methyl group is axial, one methyl group is equatorial. One methyl group is axial, one methyl group is equatorial. It's a complete tie. Your conclusion for this should be that the two chair conformations are of equal energy. And in real life, if you could freeze, if you have a jar of this cyclohexane, dimethyl cyclohexane, if you freeze the jar and say stop moving, stop vibrating, 50% will look like this, 50% will look like this. Okay. Now obviously they could go upside down, but in terms of chairs, you're always going to have one axial and one equatorial. Okay, so that's equal energy. Now, one more example, and then that's it for cyclohexanes. And the example is going to be this. Remember what group that is called? A tert-butyl group. Huge, much larger than a methyl group. You can imagine that if this dude was axial, it's going to be severely bumping your diaxial hydrogens, these hydrogens here. Okay. So just imagine if this group was super large. Now, I just want to mention that some professors kind of want you to quantify. So in this situation, I would say that there are two 1,3 diaxial strain interactions. One for this interaction here, the bumping here, and the bumping with this hydrogen to this methyl group. Okay. The last example is this one, CH3. Okay. You could pause the video and draw the two chair conformations. Let me show you how I would draw the first chair conformation. I still want to make wedges go up, and I have this. Carbon number 2 has the methyl group, and that's up also. But look, on carbon number 2, the up position is equatorial. So we have one axial, one equatorial. When I do the chair flip, carbon number 1 is still here now, and carbon number 2 is here. Up stays up, but in this case, it's equatorial. And 2, up stays up. So we have a tie, one axial, one equatorial, one axial, one equatorial. But what do you think is a more preferred conformation? Look at that group versus that group. The bigger group is axial here, and it's going to have very severe diaxial strain, 1,3 diaxial strain with which hydrogens? These hydrogens here. Okay. By putting the bigger group off to the equatorial and sacrificing the methyl group, making it axial, we actually made the more stable conformation here, even though it's a one axial, one equatorial for both. The fact that we made the bigger group the equatorial in this case makes this molecule or this conformation the more stable. Okay. Alright, that is it for cyclohexanes.